In this video, I'm going to talk about bolt hole patterns and simultaneous requirements and datum reference frames and a whole bunch of other stuff. So I got a couple examples here. Right? We're going to look at flat plates with an inside diameter, an outside diameter, and a pattern of holes. And then we're going to upgrade to the same thing with tabs. Right? And it doesn't matter what they do for right this second. So let's get into it. This first one, we're going to define it. We're going to define it like so. On all of these, datum A is going to be the flat, right? In our case, the board, near side, far side, doesn't matter. Here, I've chosen the middle as B, and I'll explain kind of why in a second. And we're going to control everything on this to A and B, right? A primary, B secondary. Well, why would you do this? Well, it depends on the function of the part. Imagine, and I'll probably use this example a couple times, automotive wheels, there's hub-centric and lug nut-centric, right? And a hub-centric, you want, say if this is the center of a wheel, you want this to fit over the hub so that it doesn't move around on you. And that's what centers the wheel. In a different kind of wheel, there's a gap right there, and the lug nut holes are going to center the wheel, right? Lug nuts, you'll see they'll have tapers. Now, automotive guys, maybe there's more to it than that, but even if I'm wrong, go ahead and imagine that's a real thing. It still makes just as much sense for our purpose here. Now, it doesn't matter for the purposes of our datum reference frame if B is the internal or the external. What do I mean by that? Let's break it down in terms of degrees of freedom A and B are taking away. Now, in each of these, I'm going to use this. X and Y. X is left right on the board. Y is up down on the board. Z is coming back out of the board right to you, the faithful viewer. Then U, V, and W are arranged like this. Little U goes with X, little V goes with Y, little W goes with Z. So if we analyze this datum reference frame, and we only have to do it once, A takes away Z, little u and little v, B takes away X and Y, right? So it doesn't matter in terms of the degrees of freedom whether we chose the internal or the external. Now, it does matter for your designs, right? Depends which one mates to something, and if both mate to something, depends which one is more critical. Now, if this is going to be used to locate, it makes sense to leave it at regardless of material boundary, right? When you reference datum B, because datum B is a feature of size, it's RMB. Datum A does not have a material condition, it's just a plane. So in this case, the ideal inspection would be you put this on a plate and you have a mandrel that expands, right? And then you find the center of that mandrel and figure out where those holes, where the outside diameter go from there. And this is a real thing, right? I've seen these with my own eyes. They have big cast iron tables where they have mandrels that expand to capture like gear housings and stuff. And so it is a thing that happens. Now, let's think about it a different way. So what if we use M and B, right? Now, this just means that we can simulate, instead of using expensive mandrel, we can simulate it with a pin. In this case, it's going to be the virtual condition. So the pin, the external pin this fits over, will be the smallest this hole can be minus the geometric tolerance. And it's possible if this hole comes in at its largest size let's just say its largest size, right? It can move on that pin, right? That's datum shift. The datum shift is just the actual size of the hole minus the virtual size of the hole divided by 2 will give you your radial shift, okay? Now sometimes, some designs that's good, some designs that's not going to work. Generally, if something is spinning, you want to use RMB. If it's stationary part, you could use MMB. Again, generally though, right? Every design is going to be different. Now let's consider the situation where this hole is going to be a clearance, right? And the outside is going to be a clearance too, right? They don't mate to anything. They're just going to mate to air, but they do need to exist. Here, imagine again, it fits over 4 studs, right? Like a wheel hub, right? And we're going to use these to center the thing, right? Now in this case, this still applies, right? Datum A takes away Z, U, and V, but we're using these 4 holes together to take away X and Y. The difference is, now this is going to take away W, right? It takes away rotation because it's 4 pins. The thing physically can't spin. Whereas if you fit it over a cylindrical pin, right, it can spin. Right? If we leave this at regardless of material boundary, right, you'll find if you flip through the Y14.5 standards, I don't know if you'll find a single example of this being done like so. They always show it at maximum material boundary, right? It's very common in the Y, especially in the older standards. Everything's MMC or MMB all the time, right? It barely ever shows regardless of feature size, which is unfortunate because that's what a lot of designs use, RFS and RMB on everything. Okay, in any case, what this means, right, in a perfect world of theoretical datum simulation or true geometric counterpart, whatever you want to call it, is we'd have 4 pins that start at the virtual condition, right, the smallest they can be minus the geometric tolerance, and they all expand, right, until the part stops moving, right? All 4 of them are supposed to expand simultaneously. Then you find the center and go from there, right? The center of those 4 pins, right? Easier said than done. But that will eliminate datum shift, right? You won't have any, right? The part is going to be 100% fixed before you take any measurements. Now, with modern coordinate measuring machines, it's not such a big deal, right? A CMM will go find those holes and build this out, and it shouldn't be that bad. And it's what you would want if the mating part is going to be similar, right? If you want these really close to the studs. Now, there's another school of thought that says, well, the lug nuts themselves have little cones on them, so what does it really matter? You can go back and forth with this, but I just really want to get across the degrees of freedom, right? The biggest difference is this is going to take away rotation about Z, although it might not really matter, as I'm going to go over with simultaneous requirements here. All right, say we've got the same design, but now we're going to add another feature, right? We're going to add these little tabs. And what I might do is repurpose over here instead of drawing this all over again. Here we've got 4 tabs, right? We're going to control them with position, but we could just as easily use profile. In any case, we're going to use A, B, right? And this works perfectly fine, because as we just talked about, B takes away rotation, right? So if you've got this thing locked on 4 pins or expanding pins, whatever, you're keeping this tolerance zone relative to that, right? Pretty simple. Now it doesn't work as well if we do the same thing up here. So I'm going to repurpose this one as well. So we're going to do these 4 tabs to A and B, but recall here B does not control rotation. Now you might say, oh geez, well what makes these tabs and these holes line up with each other? And the answer is something called simultaneous requirements. When you have the same datums in the same order and the same material condition, all the positions and profiles that share that, right, those 3 things, form a single pattern, right? Single pattern. Now what that would look like on our part, I'd like you to imagine, here's the tolerance zones for this position, right? 2 parallel planes. I'm going to draw those. Here's our datum axis. Right? Here's our tolerance zone for the holes, cylindrical. I want you to imagine the datum axis being the intersection of 2 planes here, it's got a basic 90-degree relationship. Right? We're going to call this 90 degrees. So if we've got a datum plane here and a datum plane here, those tolerance zones straddled on this plane. This tolerance zone is centered on that, right? And on and on. And that's how I try to explain it to people. Think of the tolerance zones first, right? They're all locked together with each other. Now, you might say, well, our design has 17 holes and they're all weird, whatever. It doesn't matter as long as you can get from these with basic dimensions, which you should have those on your drawing, right? They're all fixed and perfect. So if you could imagine, you feed this to a computer, you tell it, hey, here's some tolerance zones. Now go, measure the part, analyze all the data from the surface, and then see if everything fits within these tolerance zones. In any case, right, none of these are surface. I said surface a minute ago. What I mean is, in order to find the center plane of this external feature, you've got to take some points on this side, take some points on this side, and then create a plane, right? It's not going to be, ideally, in a physical world, with gauges, you'd find that center plane of the unrelated actuating envelope with the physical thing, but nobody does that, right? This kind of stuff you're going to be doing on a CMM. Holes, yes, you could use gauge pens, but most companies are going to use a CMM anyway. It's not unrealistic, in my opinion, to ask for this with just A and B. Now, if somebody's not familiar with simultaneous requirements, you can always force a rotational degree of freedom control. Again, B just controls translation in X and Y, right? We want something to control W. So we could just make those 4 tabs datum C. Right? Now datum C is going to control little w. And by opinion, you get to the same place. Right? This interpretation of your tolerance zones does not change, in my opinion. Now, this is something I've had a tough time explaining to people, and maybe I'm not doing it correctly. Maybe I missed something. Who knows? Let me know in the comments if this tracks with you. But that's how I would explain this situation. Now, I guess I drew too many figures, but hopefully you can read all that. Right? It's a pretty common, setup for, round parts. Okay, well that's it. If you enjoyed the video, please like and subscribe. Leave a comment down below.